So this. Oh gosh. Okay. This big idea: states of matter, bonding. This packet from this book is already online, and so the multiple choice and free response questions here, okay, are right here. The answers are also within that on the website. Let's see, there we go. For this big idea, this is also on the class website, so you can actually download it, you can open it. Now I will tell you, if you just want to print out the slides, some of the slides are going to look weird because there's stuff layered over everything else. But we're going to start by looking at properties based on the type of bonding. Now it's going to seem like we're skipping around because every slide is based on a learning objective. So like Big Idea 2 has a whole list of learning objectives. And these slides actually go in order, so 2.1, 2.2, all the way up. That's why it might seem like we kind of skip around a little bit. But we have ionic, we have covalent, we have network, and we have metallic bonding. Different types of bonding. If you remember, we did this. I think this was around keystones last year because I didn't see you guys every day, so you worked on this during keystones. You need to know the different properties based on the type of bonding. So, for example, ionic solids conduct electricity. Ionic and metallic are the only ones that conduct electricity. Covalent doesn't. You have different types, right? Ionic, metal, nonmetal. Covalent or molecular solids are really every covalent compound except for these exceptions like diamond, graphite, silicon dioxide. Those are really the only network covalent solids that you have. And then metallic are actually just metallic atoms. Every few slides you'll see something that says a virtual lab. If you actually go in and you click on this, it's actually going to take you through, well, a virtual lab that actually looks at identifying things based on their different types of properties. So, for example, melting boiling point. Maybe you have a question that says the melting point is high, it conducts electricity, and it's a solid. Well, that doesn't work. Or I should say the solid conducts electricity. Then you actually could look at this and you could actually figure out what type of solid it was. It would be a metallic solid. Right? We actually talked about the oxyacid strengths today in class. You really want to look at it based on whether you're looking at the number of oxygen atoms, so if it has the same central atom versus a different central atom, or if it's a binary. That actually tells you acid strength. If it's the same central atom, you look at the number of oxygens. If it is different central atoms, you look at electronegativity. And then binary acids, you look at the bond strength. Okay, behaviors of solids, liquids, gases. These are great questions to ask with particle diagrams. All right, solids, liquids, gases, and then you either heat it up or you cool it down. They could definitely ask questions about, what does this particle diagram represent? Or what phase change does this particle diagram represent? Maybe they give you two. Starts close together and they're still somewhat close but spread out a little bit. All right, so solid to liquid is what phase change? Yeah, melting. Yeah. Okay, melting. So it's just using different particle diagrams to look at the difference between the states of matter. And then we get to kinetic molecular theory. Those of you that had me last year probably remember this, especially if you were in 6-7. So, kinetic molecular theory, okay, or KMT, describes your gases. Okay, particles that are relatively far apart. Elastic collisions means they don't lose energy. They bounce right off of each other. Continuous random motion, and they don't interact. That means they don't react with each other. Okay. What is the definition of temperature? Average kinetic energy. If you don't change the temperature, you don't change the energy. Don't let that multiple choice question trick you. Right? If the temperature is not changed, the average kinetic energy does not change. No matter what else you change. Temperature is average kinetic energy. Gases begin to act real, okay, non-ideal, at low temperatures and high pressure. Okay, because when you're at low temperature and high pressure, that's when your gas molecules actually start to interact with one another. And then the stronger the intermolecular forces, the less ideal your gas is going to be. So if you have hydrogen bonding, that's going to cause your gas molecules to behave more real. It's harder to overcome those intermolecular forces. Okay, so properties of gases. You do not need to worry about the names of the gas laws. You don't need to know that, pressure versus volume is Boyle's law, volume versus temperature is Charles' law. You just need to know how they behave. So like if you increase volume, okay, so you have a box, you increase the volume, what happens to pressure? It decreases, it goes down, right? So you need to know those relationships, but you don't need to know the names. And then also know how to do the math with it. So whether you use PVNT tables or whether you use the actual, P1, V1, P2, V2, that's up to you. But you definitely need to know the relationships. Okay, ideal gas law. So here's a sample multiple choice question. I don't know where they found this picture of this dog, but I thought it was funny. So here's a question. 15.5 grams of an unknown substance are placed in a sealed 5-liter container. At 150 degrees Celsius, the substance is fully converted to a gas, and the pressure in the container is 1.10 atm. Which of the following equations represents the molar mass of the unknown compound? Okay, so talk to the person next to you. Notice you're not actually solving, but you're just showing what your setup might look like. So talk to the people next to you. All right, take a minute or two. See if you can figure out which of these would be the right answer. I do want you to keep in mind multiple choice now on this test, like on the AP test, only has 4 choices instead of 5. Doesn't sound like a lot, but...
Here. Second.
Oh, come on. Okay.
Okay, so here's the first thing to think about. If you're trying to find molar mass, what are your units for molar mass? Grams per mole. So where will your grams probably be? On the top. So which of these could you eliminate right away? A, B, and D. Oh yeah, B doesn't even have 15.5 in it. So then you're between C and E. What is the difference between C and E? Temperature. Temperature that they give you is 150 Celsius. Is that the same as Kelvin? No. Right, your answer is E. Okay, to calculate molar mass, though, you just do grams over moles. So you could solve the ideal gas law for N, do 15.5 over N. Okay, chromatography. Another big one. This is actually a learning objective. There's a B.
It has a B under the...
Uh-oh. Oops. Great. This learning objective, it actually is based on, chromatography is actually a learning objective. So they could ask you a question either in multiple choice or free response about chromatography. Okay? The whole point of chromatography, all you would have to do is explain how it works. Right? Here's how chromatography works. Paper. Okay? Paper is cellulose. Cellulose is polar. So as you're separating a mixture, something that is more polar is going to stick to the paper. So if something is more polar, it's going to stick to the paper. Something that's non-polar will not stick as much to the paper, so it's going to go up higher. So this kind of goes to that like dissolves like. Now don't use that as an explanation. You would say polar is more attracted to polar molecules, so it does not travel as high up on the paper as those that are non-polar.
Would it tell you if the thing was polar or non-polar? Would you have to find the number and be like, oh, that's polar?
No, it would tell you. Yeah, or it would say, you have water. Okay, so now back to this. We're going to look now at solute versus solvent. Right? Which of those is the solid that you would dissolve? Solute. Right? Solute is what you dissolve. Solvent is what does the dissolving. What's the universal solvent? Water. Okay, now when drawing the solute ions, okay, a couple things. This was a free response question. Pay attention to the size. Cations are smaller than anions. Okay, draw the charges on the ion, okay, because ions have charges. But you don't have to draw it on water unless you draw the partial. That's that delta. And then you need at least 3 water molecules around it. That's the solvent cage. How many could you have? Up to 6. Okay. The negative dipole, so the partial negative side, which is the oxygen, is going to point toward the cation. The positive side will point toward the chlorine. And you guys have done some stuff like this before, but just to review. Okay, then looking at molarity and looking at the particle view. Okay, this would be a type of question. I said they're starting to incorporate more particle diagrams. This says rank the 6 solutions in order of increasing molarity. Now some of them might be like tied, and that's okay. But I want you to talk to the people next to you and rank these in order of increasing. What does it mean to be increasing order? Smallest to biggest. Okay, pay attention to the volume, and some have equal concentration. So talk to the people next to you.
Oh, yeah. Wait, how many is in B? More than an A. Well, what has more? They're always
Okay, so which of these did you say have the smallest molarity? Okay, I heard C and E because this is 4 for every 50. This is 2 for every 25. It's the same ratio. Okay, so you can even you can look at the ratios. You don't need to do calculations if you can just look at ratios. Okay. Did you find one that has the largest? Yeah, look at B. Count. Right. Think of each particle as a mole. Right? You have what? 1, 2, 3, 4, 5, 6, what, 12? 12 moles in 50 milliliters. Okay, this is 1, 2, 3, 4, 5, 6, 7. This is 8 in 50. Notice A, D, and F all, oh wait, no, not D, just kidding, not D. C, E, and D, those would be equal, right? They have a ratio of 2 to 25. F and A also are similar with their ratios. And then B is going to be the most. Okay, they like to incorporate more of separating solutions. So kind of like chromatography, you can also separate solutions using distillation. You can also use Coulomb chromatography. I don't know if your review book talks as much about Coulomb chromatography, but I know that this book, I think it's under this big idea, talks about Coulomb chromatography. Right? It's a little bit different than paper chromatography. You just have different layers. So that's definitely in here too. It's just another way to separate. So distillation. What physical property does distillation take advantage of? Boiling point, yeah. Okay, so this takes into account boiling point. The one with the lower boiling point is going to separate first. So if this is water and ethanol, which of those has the lower boiling point? The ethanol, right? It's C2H5OH, mostly dispersion with 1 hydrogen bond. So the ethanol is going to boil off first, okay, because it has the weaker intermolecular forces. Okay, so you're going to heat it. Then you're going to bring it up here. It's going to condense because this is like a little cold water tube. And it's going to come down, it's going to condense into a new beaker. So now you've separated water, you've separated ethanol. If you had another solution in here, you could keep heating it. The one that has the next lowest boiling point is going to be the one that boils off, and then you would condense it down. So that's how distillation works. And then you could boil off the water. So now we're going to look at intermolecular forces. Okay. This is going to deal with London dispersion forces and nonpolar gases. So this question says, which of the following would have the highest boiling point? So thinking first, highest boiling point would mean what about intermolecular forces? Strongest. So with the person next to you, talk about which of these would have the strongest intermolecular forces. Okay, what did you guys say for this one? I C. Correct answer is C, because all of these are noble gases. What is the strongest intermolecular force in every single one of these? Yeah, dispersion forces or London forces. It doesn't matter which one you choose. Either one is going to be right. But as you're looking at dispersion forces, the stronger dispersion forces are the ones with more electrons. Make sure if you are explaining strength of dispersion forces, don't explain it based on mass. Explain it based on electrons. Right? Now, obviously you're like, well, but it does have more mass. Yeah, you're right, it does. But the reason that the London forces are stronger is because it's more polarizable because of more electrons. Okay, see, look, ta-da. Okay, so this shows you just the boiling point. Radon would have an even higher boiling point than xenon. Okay, so deviations from ideal gas. Now, this should be talking about this video up here. So when watching, if you do want to watch this video, really, or as you're doing review, don't worry about van der Waals equations. You're really just focusing on dispersion forces. So at which value of temperature and pressure will nitrogen behave least like an ideal gas, aka like a real gas? So your answer is going to be A. Okay, ideal gas law works best at high temps and low pressures. So when it's at low temperature and high pressure, it's going to behave more like a real gas. So high temp and low pressure is when the ideal gas law works best. So you use ideal gas law, well, you're going to use ideal gas law all the time because it makes your life easier. But if you're asked a question like this, gases are ideal at high temps and low pressures. They're real all the time, but they act more real at low temperature and high pressure. Okay, so hydrogen bonding. Hydrogen bonding is going to be most common. Well, here, remember, hydrogen bonds just want to have fun. Okay. I thought it was funny. But hydrogen bonding, you see it in water, ammonia, HF, alcohols, so ethanol, methanol, anything that ends in that OL, but also DNA. They asked a multiple choice question on DNA. I think it was on your guys' intermolecular forces test, where they just actually gave you DNA and they said which of the following are hydrogen bonds. Remember that hydrogen bonds are between molecules, not within. What would be a bond, like what would be the bond between the OH in water? Like what type of bond is between the O and the H in water? Covalent, right? Intermolecular forces are between molecules. A covalent bond is within a molecule. Okay, more specifically, it would be a polar covalent bond. Okay, so intermolecular forces are between molecules. Covalent or ionic bonds are within molecules. Right, as we look at solubility, okay, Coulomb's law is what you can also look at as you look at solubility. Ionic compounds dissolve in water. Water is polar because, like you guys have seen, the positive is attracted to the oxygen in water, the negative ion, the anion, is attracted to the hydrogen in water. You can think about it like a tug of war, but when it comes to Coulomb's law, the smaller the ions, the harder it is for water to pull apart an ionic compound. Okay, the smaller the ions, because think, they're really attracted to each other. So the smaller the ions are, the harder it is to pull them apart. So this says, predict which of the following should be more soluble in water. So when you dissolve something in water, okay, if it's going to be more soluble, does that mean it's easy or hard to pull apart? Easier to pull apart. All right, so you want the size of the ions to be bigger. So I want you guys to see if you can answer these three. So you're comparing Li and Na, Na and K, and BeO and LiF. Like LiF, NaF, those actually aren't going to be at equilibrium because they're strong. They're soluble completely, which means it'd be a single area.
So that's like it won't like you said it wasn't a tug of war. You said it wasn't strong, it won't be a tug of war, it would just be.
Yeah, in terms of the tug of war, that's saying like as something dissolves. Like the ionic bond is holding the ionic compound together, and the water wants to pull them apart. That's like the tug of war, where you're comparing the ionic bond to water pulling it apart, to the solidation process. Okay, so taking a look at this. For the first and second, you're just comparing size of ions. And the bigger the ions, the easier it is to pull apart. In this third one, though, right, with the first and second one, what are your charges actually in all of those ionic compounds? +1, -1. So the charges were the same. Well, what about down here now? Yeah, BeO is +2, -2, LiF is +1, -1. Which holds stronger? The one with more charge. So beryllium oxide is actually going to hold on tighter because it has a higher charge. Okay, entropy. Okay, over here again, like I said, do not say like dissolves like. You'll like get no points. Right? Instead, refer to dispersion forces, hydrogen bonding, and dipole-dipole interactions. And so that's like water. Okay, when water dissolves sodium chloride, that's because of the hydrogen bonding interacting with the positive cations and the negative anions. So which of the following substances would have the highest vapor pressure? This is going back to intermolecular forces. Okay, so talk to your groups about, or to your groups, to your person next to you, I guess. Highest vapor pressure. What does that mean about intermolecular forces? Highest vapor pressure means what? Weak forces. Okay, so you have to figure out which of these would have the weakest forces. Your answer is going to be C. Okay. The reason that it's C, okay, CCl4 is going to be nonpolar. Okay, smallest nonpolar is going to have the weakest IMFs. Mercury. Well, mercury is technically a metal. Okay, that would actually have some metallic properties. Plus, mercury is a liquid. Well, it's a very strong liquid. So you're really between C and D down here. And the smaller nonpolar molecule is going to be the one with weakest intermolecular forces. Okay, bonding electronegativity. We talked about this today. You don't need, you don't need to know these numbers, right? We talked about these numbers in class, but you don't need to know them. Really, the biggest thing is if you know that fluorine is the most electronegative, pretty much anything with fluorine is going to be an electronegative bond. Okay. Another thing to look at is the further apart they are, the more polar it's going to be. If they're right next to each other, it's not going to be as polar as if they're far apart. So which of the following bonds would be most polar? So if you look on your periodic table, look for the two that are furthest apart. Yeah. What do you guys say for this? HF. Right? They're very far apart on the periodic table. Okay. Ionic compounds. These are some properties. A lot of these learning objectives deal with ionic solids, metallic solids, covalent solids. The ionic solids are brittle. So if you if you have a block of NaCl and you drop it on the table, it's going to probably crack and break into pieces. It's because it's brittle. And that's because your ions become displaced. When they become displaced, they move side to side like this, and then like repels like. So they repel each other, they break apart. Okay, metallic properties. If you have metallic solids, really it's just like having metal atoms, like in this visual in the top left. This is like having gold atoms. Metallic bonding is sometimes hard for people to understand. So this analogy, actually, this is a really good analogy. So imagine having a bathtub and you fill it with like golf balls or ping pong balls. Maybe ping pong balls because you're like jumping in. That could be fun. And you fill it up to the top, right? So you fill, or like a baby pool or something. You fill it up completely with ping pong balls. If you think about that, would you have spaces between the ping pong balls? Yeah. Right? You'd have spaces between. That's like a metallic solid. You have space between. So then say, I guess ping pong balls might not work, because then let's say you turn the water on. Okay? And as you fill up the bathtub, so let's go back to golf balls now. The water fills in. The water fills in the spaces. And the water acts like your valence electrons. That's a metallic solid. Right? You have metal atoms, and then the valence electrons, they move around and they fill in the spaces. That's a metallic solid. And the sea of electrons, that's what allows it to move back and forth. Like a copper sheet, you can bend it, you can move it all around, it's malleable. That's because of the sea of electrons. Okay, so now let's think back to Lewis structures. We kind of talked about hybridization yesterday in class. So which hybridization would best represent the oxygen atom in the following? This brings us back to my little hand trick if you really want to use it. How many areas of electrons are around that O? 4. You have 2 bonds and 2 lone pairs. So 1, 2, 3, 4. S, P, P, P. SP3. Okay, so which of the following molecules has polar bonds but is a non-polar molecule? So you might have to draw it out, you might not have to. Which of the following has polar bonds but is a non-polar molecule? Any of them that you could cross out right away? I heard C. Okay, that's a polar bond. Anything else you could ignore? A. A is nonpolar. And that's a nonpolar bond because O and O, those are the exact same thing, has no electronegativity difference. it's nonpolar all the time.
Or if it's like symmetrical.
So yeah. So that's why E is the answer. Right? E is the answer. Okay, here's why. Draw out CCl4. What's the central atom? C. So you draw C. It is tetrahedral. Seb, look, you are ready to go.
I got it wrong this time.
Oh, you got it right. Right. C is the central atom. Okay. Then you have the 4 Cl's around. It is tetrahedral. That's what makes it nonpolar overall. But this says it has polar bonds. So each of the CCl bonds are polar. Right? Each of the CCl bonds are polar because they're far apart, yes. Cl is very electronegative. But overall, it's nonpolar. Okay, so Seb, you're going to get this one. Which of the following has a tetrahedral shape?
Oh, Sam, you got this. Come on. Come on.
You're not asking me.
I mean, I'm like, what is it? Yes. Okay, so the right answer is D. Right, you have 4 atoms surrounding a central, that's tetrahedral. Okay, this again has this little virtual lab if you wanted to do this. They're probably going to ask you questions like this in the multiple choice. They're going to give you a scenario. Right? And let's say that they say it has a high melting point, it conducts electricity as a solution, but not as a solid. What is it? Okay, so it has a high melting point, it conducts as a solution, but not as a solid. So then you would have to you need to know the properties of ionic versus covalent. It would be ionic, by the way. So this does have this virtual lab. If you actually click through, it actually says, like, let's go through and try all these properties out. Or you could just memorize them. But ionic compounds have the high melting boiling points. They conduct as liquids or in solution. Right? If I stuck, that light bulb that I have that has the prong, can you stick it in? If I stuck that into a beaker just of solid table salt, it's not going to conduct. That would be so bad. But when I put it into solution, right? When I put NaCl into solution, I put that light bulb in, it shines bright. Yeah, I wasn't going to say that, but I did. Or if I had a high enough temperature and I melted the NaCl, it would also conduct. Covalent compounds have very low melting points. Does not conduct ever. Is also insoluble in water, usually, and they're highly volatile. Volatile means if you left a liquid out, it would evaporate, like ethanol. So like first period when I spilled that ethanol all over the table and I wiped it, it evaporated right away. That's volatile. Okay, ionic compounds exist in a crystal lattice. This is called a crystal lattice. It is plus minus, plus minus, plus minus, as big as you want it to be. And it's just an attraction. So ionic compounds exist in this crystal lattice just because of attraction. Think about it like a magnet. Right? They attract each other. The plus and the minus attract each other. It's not like an actual bond, like you would draw the Lewis structure. You draw the bond in a covalent compound. This actually is just an attraction. You actually just bring them together. Okay, so example, sodium chloride, magnesium oxide have exactly the same structure. It exists in a crystal lattice. Their melting and boiling points are this, respectively. Explain why the values for magnesium oxide are much higher than sodium chloride. Kind of like what we talked about before. Mg and O, plus 2 minus 2. They hold on to each other, or they attract each other much more than plus 1 minus 1. And in order to melt something, you have to break that attraction. And then we get into alloys. We have substitutional, we have interstitial, we have heterogeneous. Right? You guys did this, I think, around the same time as keystones last time as well. Yeah. So this is an example multiple choice question. Pure silver is generally considered too soft to form useful objects. It's generally alloyed with other metals such as copper or gold. 2 alloys of silver were created with equal amounts. If the silver-copper alloy is harder than the silver-gold, which of the following would be the best explanation? Okay, so notice the difference between substitutional and interstitial. What is true of a substitutional alloy in terms of size? Yeah, they're either the same or they're very, very similar in size. Versus interstitial, which is when you put something in the cracks. So whatever you put in has to be smaller. Okay, so looking at this, the answer for this is actually going to be C. Okay, because it says that the silver copper is harder. Okay, that means that it's harder to break. Okay, and so that's because when you have the silver copper, okay, there's a difference in size, harder to break. Here are the different types of alloys. All right, substitutional is when you have similar sizes. Okay, so substitutional alloys tend to be malleable. They have similar densities. They're ductile, so you can pull it into thin wire. Interstitial alloys is going to be a much more rigid structure, a lot harder to break. That's like steel. Steel is iron with carbon. Typically with interstitial, you're going to have typically a non-metal substituted. Not always, but typically. And then heterogeneous, you can actually have different phases if you want. So you could actually have, like sometimes you put gas into it to change the properties. Intermetallic isn't usually used. The difference is metallic, so you have different metals that you're putting in. Okay, so then metallic solids. Remember that metallic solids are metal atoms. Okay? Like if it says iron, that's a metallic solid, not ionic. Ionic is your metal, non-metal. And this actually shows, substitutional alloy, similar in size with copper and zinc, versus steel. That's an interstitial alloy. So we also have semiconductors that we talked about. We talked about doping. One type of semiconductor is a germanium crystal, adding some impurities. Okay? It increases the conductivity. That's the whole point. Semiconductors are in your cell phone. Makes your cell phone work. Adding which of the following would create a p-type semiconductor with increased conductivity? So you have germanium, you want it to be p-type. Positive. Just think about that. That's not like the actual, but think about P is, you want it to be positive, N would be negative. So you could have P-type versus N-type. Right? Your correct answer is going to be D. Because this is why a p-type semiconductor, right? That means you go through p-type doping. I say remember P is positive, so you need something that has fewer electrons. Think about positive. You want it to have fewer electrons, so you want to dope it with fewer electrons. So germanium has 4 valence. You want to pick something that has fewer than 4 valence electrons. N-type means you want it to be more negative. So you want it to have more valence electrons. Okay, covalent compounds. Graphite versus diamond. This is looking at covalent network. Right? Notice graphite is a covalent network. Diamond, not. Well, technically diamond is a whole thing of its own. Graphite, though, are sheets. It exists in sheets of carbon atoms. Diamond, it's all intertwined in a 3-dimensional structure. This is what makes diamond so strong, so hard. That's why you cannot break diamond unless you have a lot of force. Okay, so with covalent solids, this was actually a free response question on last year's test, I believe, or 2 years ago. Okay, so you have plastic beads that are either polypropylene or polyvinyl chloride, PP or PVC. You really don't need to know a lot about organic. You're only looking at what's in these parentheses. Okay, you add those to a beaker. After stirring, you observe one of them sinks, one of them floats. Based on these pictures, on these diagrams, which one is which? All right, so given the spacing, the beads that sink are which of these and why? It says to explain. If you're thinking about sinking, what would that have to deal with? Density. Okay, so which of these, they're the exact same size, right? It doesn't say anything about the beads being different size. So if the size is the same, then what are you going to focus on with density? Molar mass. Okay, which of these, you have essentially C2H3CH3 or C2H3Cl. Which of those is going to have a higher molar mass? The one with the Cl, right? PVC. So PVC is actually going to be the one that sinks. Floating and sinking means you're looking at density. Okay, molecular compounds. So the covalent was talking about covalent network. Now we're looking at molecular solids. So we really can have one of two things. We can have something like water or something like iodine. These both are molecular, but what type of intermolecular forces exist within water? Hydrogen bonding, which means if you have hydrogen bonding, you also have dipole-dipole. And what do you always have? Dispersion. Where I2, what exists in I2? Only dispersion. Right? So which of the following are broken when water boils? You can have more than one. It's not just one answer. All except covalent. Please don't say that covalent bonds are broken when water boils. Okay. Water boiling is just a phase change. In order to break the covalent bonds, you would actually electrolyze water. Hook it up to a battery. You actually bubble off, kind of like you guys did in the lab. Explain why iodine is a solid with a low melting and boiling point, almost insoluble in water, but soluble in organic solvents. Okay. Organic solvents typically are made of what? C and H, and maybe O. Normally C and H. What intermolecular force exists between C and H? Dispersion. Right? And is also a non-conductor of electricity. So just to save a little time. Iodine, okay, is I2. What intermolecular force exists in I2? Yeah, dispersion, right? I2 molecules are held together with dispersion forces. So that means that I2 is pretty weak in terms of intermolecular forces. Right? Dispersion forces are easy to break. Sometimes they break at room temp. Okay? It's almost insoluble in water. Notice as we go through this, it says to actually explain each of these. So if this were a free response question, make sure you hit every single one of these. So explain why it has a low melting boiling point. That's intermolecular forces. Explain why it's almost insoluble in water. Also intermolecular forces. And why it doesn't conduct. Well, intermolecular forces. Kind of. So it's almost insoluble in water because what are the only attractions that would exist between the water and the iodine? Yeah, dispersion, right? You can't hydrogen bond between H2O and I2 because I2 can't hydrogen bond. So it's almost insoluble in water because the only way that you can get them between each other is with dispersion. And you have to try to break hydrogen bonds in water, and water doesn't want that. It does dissolve, though, in organic solvents like hexane. Hexane is C6H12, all C's and H's. All you have to do to get iodine to dissolve is break dispersion forces in hexane, and that's easy. dispersion forces are weak. And iodine doesn't conduct electricity because it's a molecular solid. Right? It's a molecular solid, so it doesn't have electrons that move around.